All right. Well, hi everyone. Let's get started. Welcome to this new seminar of the Exoplanet for 2022 seminar series. My name is Maxime Maurice. I'm a postdoc at Rice University, and I'll be your host for today's seminar. Before I introduce you our speaker, our little ritual as usual, I will say a few words about the Exoplanet project, which is hosting this seminar. Here we are. Exoplanet is a multi-institutional interdisciplinary initiative to unravel the conditions of planetary habitability in our solar system and beyond. And its lead institution is Rice University, and it is supported by NASA as one of the team of the Nexus for Exoplanetary System Science, Nexus, Coordination, Network, and Astrobiology. And then we also find it important to acknowledge that our research at Rice University is pursued on the traditional lands of several native people, namely the Karankawas and Sanas, as well as the Coahuiltecans, which are represented today by the Tapilam Coahuiltecan Nation, and the Ishaks represented today by the Takapa Ishak Nation. We see it as our duty to acknowledge this historical aspect of our identity and to foster a beneficial environment for all communities, in particular those who preceded us on this land. And with that, that's my great pleasure to introduce you our speaker for today, Professor Emily Rauscher. Professor Emily Rauscher is an associate professor at University of Michigan, and she is an expert in characterizing the atmospheres of exoplanets. And that's what she's gonna tell us about today. So Emily has been through most of the American territory through her scientific career. She started a BA in Berkeley, I think, and then went to the East Coast in Columbia, right, for her PhD. And then she was a NASA Sagan Fellow in a few other universities, University of Arizona, as well as Princeton, right? And since September 2015, she is a professor at University of Michigan. And the talk for today will be pushing the boundaries of exoplanet atmospheric characterization. So as usual, if you have questions, you can write them in the Q&A, or you can hold them until the end when you will be able to raise your virtual hand, and you will be allowed to speak. So with that, Emily, the floor is yours.
Great, thank you. Let me get this set up. And you can see my slide okay?
Yes.
Great. Okay, well, thank you very much for the introduction and the invitation. I realize this is an interdisciplinary group, so I'm hoping not to get too much into jargon. Instead, I want to give you a taste for my very biased view of where the boundary is in terms of what we can measure in exoplanet atmospheres. And in particular, I'm going to focus on two of my favorite techniques for making atmospheric measurements of exoplanets and talk about some of the particular properties that we get to measure with these different techniques. I should also say at the outset, I'm not an observer. I don't like touching data myself, but as you'll see in the talk, I'm very excited about cutting edge data and the things that we can learn from them. My particular specialty is three-dimensional modeling of exoplanet atmospheres and then linking the predictions from those models to different observational signatures that we can hope to measure. So I will start with a little bit of contextualization. So here we see, only about a month old, I guess, a plot of how many exoplanets we have detected as a function of time. And of course, it's cumulative. So you see the number rising over time. It's color-coded by detection technique. I'm not focusing on that so much today. But of course, one of the takeaways is that we now know of over 5,000 planets orbiting around nearby stars outside of our solar system. And there's much interesting science that can and is being done with these exoplanets and pushing the boundary in terms of discovery. But I also want to start marking on this timeline some of the things that we've been able to do in terms of characterizing exoplanets. And by that, I specifically mean measuring properties of their atmospheres. So a couple of the first major measurements for atmospheric characterization came in the early 2000s, I guess is that decade, measuring the first atmosphere and the first light emitted from an exoplanet. I'm not going to review kind of all the different ways that we can measure exoplanet atmospheres, because luckily there's too many now to do that very quickly. But instead, I'm going to focus on how 3D properties can show up even in some of these most basic measurements. So let me give you a little bit of context there. So this diagram shows the geometry that we're usually dealing with when we're trying to measure exoplanet atmospheres. Because there are some exoplanets that are far enough from the star that you actually can spatially separate their light from the star and measure an atmosphere that way. But that's a significant minority of systems. In most cases, we are actually not able to visually separate the planet from the star. And so instead we use different tricks to separate the planet from the star. And in this diagram, we see that one of our favorite sorts of systems are these transiting systems, because they give us multiple opportunities to measure different properties of the planet. And I'll come back to this, focusing on some more specific parts of this later. But we can make a measurement, for example, when the planet goes into eclipse behind the star, and we see a little loss in light. That was the light from the planet. And if we make that measurement with, if we make a spectrum, then we're getting the spectrum emitted from the planet. Great. But we can get ourselves into danger depending on how we interpret those data. So there was this nice work some years ago that said, well, let's assume that when we observe the planet, there are two different regions on the planet. Here they're labeled day and night, but maybe you just have one region that's hotter and one region that's colder. And so I realize it's a little bit small, but the top set of panels are showing you the pressure temperature profiles for those two different regions. So this is the one dimension that I'm talking about, temperature as a function of pressure or height in the atmosphere. And so each of these different regions then has a spectrum, an emitted spectrum associated with that region, and that's shown in the second set of panels. And in observation, those two would be combined. We would integrate over the whole planet disk, and we'd see a combined spectrum. Okay, so then what happens when people actually measure secondary eclipse spectra is they then try to fit a model to those data to figure out what the atmosphere is like. And this little animation shows an example of how you might run an MCMC fit, where you're varying a couple parameters in your model and calculating spectra and comparing those spectra to the data and exploring parameter space until you find a maximum likelihood solution and some estimate of your uncertainty on these different properties. Here, it's gas abundance and temperature, but there's different parameters that could come into play. And so this is typically what's done. We get some data, we try to fit it, and you can use whatever model you like in this fit, but usually it's a 1D model because 1D models are fantastic. They're kind of the most straightforward way that you can characterize an atmosphere. And there are situations where they can be very appropriate. But in this little simulated setup that we have, if you have enough of a difference between the hot and the cold regions of the planet, and then you try to fit your simulated data, assuming that the planet just has one temperature profile, that's shown in the red set of curves here, or has two different temperature profiles, shown in the blue, you get very different answers. So each of these little panels, I've hidden all the information from you, but each of these little panels is showing you that same sort of region you just saw in the cartoon, kind of how well we think we're measuring some different parameters in the atmosphere, in this case, abundances of different molecules. And the correct answer for each parameter is marked with this little dashed line. And of course, the blue fit does a good job of recovering that because you have two components underneath, but the red fit does not. And worse, the red fit thinks it's done a good job. The red fit thinks we're tightly constraining some of these abundances, whereas it's not getting the right answer, and not even within its own error bars. So how much this matters or not depends on two things. One being the inherent spatial differences around the planet, and the other being the sensitivity of your data, right? So maybe you have huge temperature differences, but your data have huge noise levels. Oh, well. And so it's these two things in balance that set how much we need to worry about this. I'll also point out that the other kind of main way that people have measured exoplanet atmospheres comes in transit with the starlight that gets filtered through the planet's atmosphere. And there have been similar studies showing that you can also get biased results if you have inhomogeneities around the planet in that situation as well. Now, for some planets, this may not be so much of an issue. But for the planets that are the most common type of target for atmospheric measurements, this actually, I think, is a big problem. So most of the planets that we've measured atmospheric properties for are this type of planet known as a hot Jupiter. So a large gaseous planet sitting several stellar radii away from its host star. And these planets are very 3D. I mean, I suppose any planet is 3D, but hot Jupiters are especially 3D. They have huge temperature gradients between the day side and the night side. This drives very fast winds around the planet. So within a single atmosphere, you're crossing interesting physical regimes from kind of more classical planetary contexts to things local conditions that are more similar to stars. So I could give a whole other colloquium about some of the interesting things in modeling these atmospheres, but my point in this talk is to just impress upon you that hot Jupiters are best targets for atmospheric characterization. They're the biggest and the brightest, and observers love them, and they're inherently physically very interesting. But they're also kind of the type of planet where we need to worry the most about biases showing up in our data. However, because they have such large three-dimensional differences, and because they're always the target that we're going to use with any new atmospheric characterization technique, they provide us with an opportunity to see kind of the level of detail that we can actually measure about these atmospheres, hopefully in preparation for measuring more and more detail in cooler and smaller planets in the future. So we come back to this little timeline that I've put here. And aside from these first couple of detections, which was a transit observation and a secondary eclipse observation, along with discovering more and more exoplanets, we've also developed more and different techniques for measuring different sorts of properties of the exoplanet atmospheres. So, for example, we can measure spatial differences around the planet. So not one dimension in pressure, but actually around the planet's day side and night side, or a two-dimensional map, which I will talk about at length. And there's also been techniques, which is the second technique I'll talk about, that let us measure velocities within exoplanet atmospheres. And so rotation rates and winds are also a complex property that we're starting to be able to measure. So that's my contextualization. And now I'm going to focus on two different techniques. First, eclipse mapping, which is how we do this 2D mapping of exoplanets. And then I'll talk about high resolution spectroscopy, which is how we measure these velocity components. And then I'll try to tie it back together a little bit. So eclipse mapping. This is a technique that is really about to take off with the launch of JWST. The first JWST eclipse map is done and being written up as we speak. And so this new facility is enabling this technique in ways that were previously not possible. So this technique uses the same sort of idea as the rest of the implicit observational techniques diagrammed here, where again, we can't visually separate the planet from the star, but we know where the planet is in its orbit. And so we can use changes in time to measure properties of the planet. It goes behind the star, we see a dip in light, we've measured the emission from the day side. It goes in front of the star, we see absorption from the planet's atmosphere. And of course, there's phases observation as well, which is a whole nother interesting thing that I don't have time to talk about. Each of these changes in time is also associated with a change in space in some sense, right? So the phase curves, for example, as time is changing, we're seeing different spaces on the planet. And eclipse mapping uses the same idea. It focuses on these regions of ingress and egress, and it uses the limb of the star to scan across the disk of the planet. And if we can measure our loss of light or recovery of light very carefully during that time of ingress and egress, then that is providing us information about the gradient of brightness across the planet disk in the direction that the stellar limb is scanning. So this is a technique that's been used in other areas of astronomy as well, to use occultations of one object to scan another. And for exoplanets, we have published so far one map of one planet. And this is what it looks like. It's a little hard to say we have one map because actually two different groups independently analyzed the same data set and produced maps that are in agreement. So this is a hot Jupiter that we're mapping, and these observations use the Spitzer Space Telescope at 8 micron. And so the map from one of the groups is shown on the left and the data are shown on the right. And so you see, actually, we have measurements of the secondary eclipse there. This is light versus orbital phase or time. And so we have information during those ingress and egress stages, but we also have a lot of information actually as the planet is just rotating before it goes into secondary eclipse. And so for comparison, the blue curve shown on the data would be if you had a uniformly bright planet disk, and obviously that's not the case. This is not the best way of showing the information during ingress and egress, but it shows you the data, which also look kind of noisy. We'll get back to that. However, back in 2012, when these results were first published, it was already apparent that eclipse mapping is pretty tricky in practice. And this is fundamentally because you're going from a measurement that is one dimension. You're measuring light versus time. and you're trying to create a second dimension so that you have, for example, brightness versus longitude and latitude on the planet. And so you have to use some kind of assumption, you have to use some kind of mapping to pull that spatial information out of this measurement. And the paper by DeWitt in particular focused on, actually there's even more interesting nuance in this paper beyond what I have time to talk about, but one of the complications is that the map that you get out depends on the structure that you assume for the map. And so here are a couple comparisons from that paper. Both good fits to the data, but using different frameworks for how to describe the brightness distribution on the planet. On the top, this is a model that uses spherical harmonics to describe the brightness distribution across the planet, up to a degree of 3 in this case, and it allows for kind of shifting of latitude, longitude, location of the spherical harmonics, if you're trying to decode what that equation means. And then on the bottom, this is a different mathematical assumption for what the brightness distribution on the planet could look like that's a little bit more informed by physical expectations for what we think the brightness structure should be. So you have a hot region with some width in latitude and longitude and some center location. And so you see that there's some properties that are in agreement between these fits, but obviously they don't look identical and there's important differences. So part of the reason for this is that the map on the planet is not the same as the map that we're observing. And when we fit, we really would like to fit orthogonal components so that we don't have degeneracies between our different fitting components. And on a sphere, spherical harmonics are, of course, a set of orthogonal components that are a fantastic way to describe a brightness distribution on a planet. If you can get to a high enough spherical harmonic degree, you can make any pattern that you like. The problem is that if you take the spherical harmonics and you calculate the observed light curve and secondary eclipse that would be associated with each of these spherical harmonics, those light curves, which are what you are observing, are not orthogonal. But we can fix that. And the way that we can fix that is we can use principal component analysis. So this is just a little silly cartoon to remind you that this is a technique that in 2 dimensions looks very simple. You take some spread of points, some spread of information, and you can use matrix math to figure out that most of your spread is defined along 1 dimension, and then you can find the orthogonal dimension that describes the next amount of spread. You can do this in higher order dimensions, and you can also do this with light curves. And so what we did was we just developed a technique where we use spherical harmonics as an initial basis set for the light on the planet. And you could use any basis set. Spherical harmonics is nice. You could use pixel maps. You could use whatever you like. You just want it to be a good comprehensive basis. And then we calculate light curves from those maps. And then we take the light curves and we run a principal component analysis on the light curves. And what the PCA does is it then calculates a new set of light curves that are now orthogonal to each other and ranked in order of how large of a signal they could potentially induce in the data. And so they're sorted in terms of how maximally informative they can be. And all of those, what we call eigencurves, are linear combinations of the spherical harmonics through the coefficients found by the principal component analysis. And so what this means is we can use these eigencurves to fit to our data, and we're not assuming anything physically. We're just looking for what should be the most detectable signatures in the data. And because they are a linear combination of spherical harmonic curves, we can use those same components to translate back to a linear combination of spherical harmonic maps that each curve corresponds to. And so each eigencurve has an associated eigenmap. And when we fit these eigencurves to a data set, that component on the curve is the same strength component that we apply to the map, and then we can sum the maps and we've got our fit. So there's even extra information, interesting nuance here. You have to worry about orbital elements, and it's a lot of fun. The math of it is really interesting and nuanced and fun. But we've kind of figured out what we think is an optimized technique for doing this mapping. So then enter JWST. So on the left, I'm showing an analysis of trying to figure out whether we could do eclipse mapping with Spitzer back before that 2012 measurement, just to give you an example of kind of simulated Spitzer data and how noisy it was in comparison to these two different curves that we're trying to measure a difference between, versus the plots on the right are from a simulated analysis of JWST data before the telescope launch, showing that the precision of JWST now should really be great for eclipse mapping. We should now be able to nicely differentiate between different possible structures when we apply this technique to hot Jupiter planets. But this is due in large part to JWST being a larger telescope, so we're collecting more photons, we have more precise measurements. But Spitzer was a measurement done at a single wavelength, a single photometric band. And with JWST, we of course are also going to have spectral information. It's not a very impressive plot I put up there, but it was a reminder to myself to make sure to say that. And the point of emphasizing that we're going to have spectral information at different wavelengths with JWST is that if we're making maps at different wavelengths, those different wavelengths are probing different depths into the atmosphere, which means that our maps actually contain three-dimensional atmospheric information: latitude, longitude, and depth into the atmosphere. But as I just described a little bit of the nuance that goes into making a two-dimensional map, making a three-dimensional map also increases the nuance and complexity of our technique. So over the last couple years, I've worked with folks on a couple different techniques that we can use to do three-dimensional spectral eclipse mapping. And both of these start with that same two-dimensional mapping technique that I just described. So it's maximally informative, not making any physical assumptions, just letting the data tell us what the most spatial information we can learn about the planet is. And we can do that at different wavelengths. And so then we have different maps of the planet at different wavelengths. What do you do with that? Well, there's one technique, work led by Megan Mansfield, where you take those maps and you think about it as a data cube now, where your three dimensions are latitude, longitude, and wavelength. And you can do what's called k-means clustering to look for places in that data cube where you have similar patterns. I'm skimming over the complexity, but the point is that at the end of the day, what you arrive at are spectral maps. So this little inset is showing you an example where your algorithm has decided that near the center of the planet, there's a region that has one spectral component that looks different from the region farther from the center, which has a different spectral component. And it returns what those spectral components are. And then this is nice because it's model independent. And it then lets you try to maybe fit those models with different physical models and figure out, maybe you're seeing that the hotter region near the center is depleted of water, for example, or maybe you find one part of the planet is clear and one part of the planet is cloudy. This technique would be sensitive to those. The other option is to actually try to get that 3D temperature structure. This is just saying what the spectra look like in different regions, but maybe you want actual three-dimensional structure. And so work led by Ryan Challoner then takes these maps at different wavelengths, and I realize the details here are too small to see, but it takes these maps at different wavelengths and then it puts them at different depths in the atmosphere, runs radiative transfer through the atmosphere, and compares the emitted spectrum to the observation. And does an MCMC fit to try to optimize the vertical placement of those maps. And you can either have them at fixed pressures, which is probably not the case, or there's different ways to let the maps sit at slightly different pressures because your opacities can change with location. It's very complicated. But Ryan also released this code as open source, so anybody is welcome to go play with it and try to make their own 3D maps. So on the left, this is an example of my reanalysis of the Spitzer data. And the point of this is that basically there were two map components that were warranted by the quality of those data. However, I can't show you the results yet, but the transiting exoplanet early release science team is currently working on putting out the first dayside secondary eclipse measurement of a hot Jupiter, so a spectrum and an eclipse map. And there's 5 components that are warranted to be fit in that map. So the answer is some combination of all of these things. So stay tuned. That should be out hopefully fairly soon. So a very large advancement in technique. Okay, so I need to speed up a little bit or maybe skip some information because I love eclipse mapping and talk about it maybe too much. But in time I can, I will tell you some things I'm really excited about with this other technique, high resolution cross-correlation spectroscopy. This is a technique that uses large ground-based telescopes. So it's nice, we have very complementary different methods here, different techniques, different types of information, different facilities. Instead of getting the planet's signal by looking for changes in time, this technique gets the planet's signal by looking for changes in velocity, which, thanks to the Doppler effect, mean changes in wavelength. So you take a spectrum of the planet plus star, looking through the Earth's atmosphere, but the planet is zooming around the star on its orbit, and so its spectrum is Doppler shifted back and forth with time, versus the star spectrum and the Earth's atmosphere lines are relatively stable with wavelength over time. And so you can use this trick to try to find the planet's signal. In this little cartoon, the planet's signal is visible by eye. Usually it's smaller than the stellar noise. And so in fact, what you have to do is you have to guess what you think the planet spectrum looks like, and then do a cross correlation of the planet's spectrum across the data and look for where you detect a signal. And if you use a good spectrum, a good guess for the planet's spectrum, you'll see a strong signal if the data allow it. And if you have a bad guess for the planet's spectrum, you won't find a significant detection. We have to do this at high resolution because you need to get that planet's orbital motion in order to detect the planet in the first place. So for hot Jupiters, orbital motion is on the order of 100 kilometers per second. And so at resolutions of 30,000, you are easily detecting that. However, the planet's not just orbiting, the atmosphere is also in motion, and the rotation rate of the planet is on the order of a few kilometers per second, as are the wind speeds. Again, this is for hot Jupiters. So at the very highest resolutions of our spectrographs, you start to be sensitive to those velocities. You can do this in transmission or emission, and you measure different sorts of things. I think I'm going to skip over this in the interest of time and dive into a little bit of detail what we get from these techniques. So in transmission, you do this observation as the planet is in front of the star and starlight gets absorbed by the atmosphere. This was the first application of this technique back in 2010. And after the orbital motion of the planet was subtracted off, there was a residual, not statistically significant, blue shift left over. And so the authors proposed that maybe this would be the kind of signal you would expect to see from winds on the planet, blowing from the day side to the night side, which is towards you as an observer during this geometry. You can also think about lines being broadened during from the rotation of the planet, and so shifting and broadening can come from winds and rotation. You notice I've said winds are the first order effect, but I've put this little footnote or lofted note that rotation also matters, right? These are similar speeds, and of course, winds and circulation and rotation are all physically combined. So yes, yeah, okay, I'll go into this a little bit. Okay, so let me step back here for a second then. So what this plot is showing is an analysis that was done on some CRIRES data where the planet's template spectrum, because remember, you need to guess this template spectrum in order to detect the planet signal. The template spectrum was compared to the data with different amounts of broadening applied to the lines. And so this broadening could be associated with some rotation rate for the planet. And so in this work, they fit the broadened spectra to the data. And whenever this fitting is done, remember the detection is using velocity. And so the results are often reported in velocity space. And so what you see here on the vertical axis is the orbital velocity of the planet. That's going to change how strongly the planet's spectrum shifts with time during your observation. And so you try different values of that during your fit. And then on the x-axis here is the amount of broadening, the rotational velocity. And in this work led by Matteo Brogi, there's a preferred region of space where that plus sign is the known orbital velocity of the planet and assuming synchronous rotation for the planet. But the neat thing about having a 3D model is that we can calculate the velocity throughout the atmosphere from all the different winds, assuming different rotation rates if we like. And so we did that to compare to high resolution data and figure out whether we could really detect these velocities and what we were seeing in them. So in this work, we ran 3D models with a bunch of different rotation rates. We think these planets are probably tidally synchronized. So you have a constant day side, a constant night side, and your rotation rate equals your orbital period. But it wouldn't be hurt to empirically check this. So here you see an example of a slice through the planet's atmosphere showing the line of sight velocities due to winds and rotation at different regions around the planet's terminator. So the starlight filters through the atmosphere and the opacities locally are Doppler shifted based on your velocity structure. And so then you get a simulated spectrum like what's shown here, where you're absorbing light at different wavelengths. And if you look kind of carefully, you can see that by turning on and off different sources of Doppler shifts, we can see the lines shift around and broaden. Now, in reality, this is not what you're measuring, right? You have a template spectrum that you're comparing to your data. And that also lets you combine the information from all these different lines. And so in theory land, with no error bars, we can do something of the same where we take these different spectra and we cross-correlate one with Doppler shifts to one with no Doppler shifts. And that gives us a way to measure the overall Doppler shifting and broadening in the spectrum. And so we get something like this, a cross-correlation function, where you see some amount of broadening that you would get anyway without Doppler shifts. That's the black profile. And then we can see that winds and rotation and winds plus rotation induce kind of a complicated broadening and shifting to the spectral lines overall. So we can then take those simulated spectra, or we did take those simulated spectra. This is work, by the way, led by Aaron Flowers. Take those simulated spectra and use those from the 3D model with all the Doppler effects in cross-correlation with previously published CRIRES data. And here's the result. Again, you see it in velocity space. As in the previous example, we were testing different rotation rates. So we have different rotational velocities plotted along the bottom. And then on the vertical axis, this is the rest frame velocity of the planet. So after subtracting off the orbital motion, this is any leftover velocity. And we believe the planet should be orbiting according to gravity, and so that should be 0. And in fact, you see this star indicates 0 rest frame velocity, and if the planet is synchronously rotating, this is the rotation rate that it would be. And our models agree with the data for this velocity value very well. Great, and we detect the planet very significantly. Yay, the 3D models aren't completely wrong. But the interesting thing that we can do is we can turn off the Doppler shifts from the winds or the rotation or both and see how that changes our answer. So here is the result that we get when we match these spectra to the data. But in this case, the spectra have no Doppler shifts from the winds. They still have broadening from the rotation, but we've just turned off the part of the velocity field from the winds. And what you see is 2 interesting things. One, the fit to the data now wants to give the planet an anomalous blue shift. This is like in that first early result that I showed you, except here we can link that really directly to the wind components in the atmosphere. To get the velocity of the planet correct, we need to have these winds turned on. The other thing you see is a narrowing of our confidence contours in the rotation space. And so if you didn't think about winds, you would think that you were doing a better job of constraining the rotation rate of the planet than you actually are. The reason being that the winds in the atmosphere are complicated, but one main component of the winds is eastward flow in the same direction as the rotation. And it happens that if you slow down the planet's rotation rate, the winds end up speeding up. And if you speed up the planet's rotation rate a little, the winds end up slowing down a little. And so that's why you have kind of flat confidence contours on the left when you include both of those effects, but that's missing from the right. And so this is an example of how you need to really be a little bit careful in thinking about what information you actually really are measuring, and the 3D models help us investigate that. We can also play a similar sort of game if we think about emission spectra from the planet. So these are observations that can be done actually at any orbital phase. This is just the light coming from the planet, emitted due to its thermal properties. And so this is work led by Haley Beltz a year ago, I guess. And again, a set of 3D models, different rotation rates, and calculating simulated spectra with all these different Doppler shifts. And so the spectra you see here are emission spectra at very high resolution over a very limited range in wavelength. And the, let's see which is which, the dashed lines, I guess, are the lines without any Doppler effects, and the solid lines include Doppler effects from winds and rotation. And you'll notice for the longer or rotational period models, those at the top, that they have similar amounts of broadening. It's again the same effect, that the winds and the rotation kind of balance each other out, it turns out. But anyway, there's a lot of interesting information in this paper, including tests. You can make different assumptions about the abundances of species in the atmosphere and chemical disequilibrium or mixing these things. And so here's a table showing a bunch of different spectra that were tested to some previously published CRI-RES data for another hot Jupiter. And you can see we compared 3D models, 1D models, different molecules, different assumptions about chemistry. But you notice the best detection with a 1D model from this analysis from a suite of hundreds of 1D models, the best detection of the planet was at about 5 sigma. When we compare that to the detections we get using 3D models for this planet, we can improve the detection of the planet by quite a lot, to almost 7 sigma. And there's lots of lines that you could be reading here, but the main takeaway is the biggest effect we found is from just having different regions of the planet with different temperatures, and so they're emitting different spectra. Okay, so lots of interesting secondary effects that both of those papers, as well as other works in the field, are finding in terms of what shows up at high resolution. But what does the future look like, right? For eclipse mapping, Spitzer was the past, JWST is the present. For high-res spectroscopy, telescopes, like the Very Large Telescope, are the present, and the future are the extremely large telescopes. This is a figure from the METIS science case. This is one of the instruments on the European Extremely Large Telescope, comparing the capabilities of CRI-RES on the VLT with METIS on the ELT. And the takeaway is that for hot Jupiters, this bottom right panel is predicting that we should be able to not have to use cross correlation. We should actually just be able to recover the planet's spectrum itself at high resolution. So what would this enable? The answer is we don't really know. Nobody's run very detailed tests yet of what we will be able to measure for exoplanet atmospheres at high res with the ELTs, but I have a couple guesses or things I'm interested in. One is thinking about what we measure in transmission. So again, light filtering through the planet's atmosphere when the planet is in transit between us and the star. And a decade ago now, we first tested the sort of signals that you might uncover at high resolution. So you see some simulated spectra we calculated, and the plot on the bottom here shows the net Doppler shift as a function of time as you observe. And so during transit, for most of this plot, there's a slight blue shift. We've talked about that before. During ingress and egress periods, when only part of the planet's atmosphere is in front of the star, you get different shapes for the net Doppler shift versus time, because you're spatially isolating different regions of the planet's terminator. And this actually is an effect that people are starting to see now in current observations. There's a bunch of papers I would love to tell you about if I had time. But another thing that we thought about is if you isolate the strong lines in the spectrum from the weak lines in the spectrum, those are coming from different heights in the atmosphere. And we found that you have different Doppler shifts associated with stronger or weaker lines, which is directly related to having different velocity fields from your atmospheric circulation at different heights in the atmosphere. So if you can isolate these lines, you can actually get a constraint on the vertical wind shear. And here in particular, we were comparing models with or without some magnetic effects that produced different predictions for the vertical wind shear. This is something I know people are working on right now. So I don't know that we have to wait for the ELTs for this. Similarly, and I'm almost done, with the ELTs, we should be able to do this, and maybe we'll be clever and figure it out sooner than the ELTs. But this is an example of a recent result with IGRINs, looking at emission spectra from a hot Jupiter. And in velocity space here, you have the planet's orbital velocity on the vertical axis and the rest velocity, which again should be 0, on the horizontal axis. And what you see is that if you isolate spectral lines from different species in the fit, you get different parts of velocity space that your fit wants to be in. What does that mean? Why would that make sense? Well, this is an example of a slightly different situation where you have clear regions and cloudy regions on a hot Jupiter. But what you can see as you're watching the planet move around and you're watching brighter or dimmer regions pass across the planet's disk, you'll also see these red and blue line of sight velocity contours. And so you could imagine, for example, if you had one part of your planet depleted in water and one part where the water was more present, then you might expect stronger water lines preferentially on the red shifted or blue shifted side versus a different species might act differently. And so I'm also excited about this in terms of pulling out more spatial information and complexity. And I will skip that. So I just talked about a whole lot of things, some really beautiful complexity, but how can I simplify it back to you? If you're just waking up now, what is the point? I would say that with these cutting edge techniques for atmospheric characterization, if we don't take 3D effects into account, at least for the hot Jupiters, where we know that there are huge 3D differences, we risk getting our measurements wrong, thinking we're measuring something correctly, but we're not. However, this is also an opportunity. If we can really interrogate how these 3D properties show up in observations and the most reliable ways to analyze the observations, that lets us access really interesting spatial differences around the planet and really strongly constrain our models and the atmospheric physics going on. And so with that, I will just put up a final slide emphasizing some of the points I made, the different techniques I talked about, and reminding you of the names of some of the early career researchers whose work I highlighted. And I am now happy to take any questions.
All right, thank you very much, Emily. Very interesting talk. We can all clap behind our screens. So yeah, the floor is open to questions. If you have questions, once again, you can either type them in the Q&A or raise your virtual hand, and you will be allowed to speak. So maybe I can start with a quick one, which is how. So you mentioned, of course, then hot Jupiters, and say that I guess we usually think of them as being tidally locked. How important is, well, I can imagine that's quite important, an assumption, and you've been talking about that, but would there be ways to like still use these techniques for planets which might not be tidally locked, and could we learn some things maybe about their rotation? Well, you spoke about the rotation, of course, but yeah, how could we extend to the realm of non-tidally locked planets?
Yeah, there's multiple ways I could answer that. It's a really good question. So I think there's none of these techniques require a planet to be tidally locked. So the good news is you can use these techniques on any planet you like. For the eclipse mapping, if you no longer know what the rotation rate of the planet is, then it's harder to translate from your light curve to spatial information on the map, on the planet's map. And also, if you get non-zero obliquities, it also makes life more complicated. Arthur Adams is publishing right now an interesting paper about how eclipse mapping changes if you change your assumptions about rotation rate. For high resolution spectroscopy, you are sensitive to whatever broadening you're sensitive to. And actually, as you move to planets farther out where tidal effects haven't locked them, you may expect faster rotation rates. And this technique has been applied to Beta Pec B, which is a directly imaged planet and young, and in fact is rotating quite quickly. And so you can see some significant broadening in that planet spectrum. And so that's the rotation rate that we have reliably measured for an exoplanet.
Okay, thanks. And so to follow up on that, I can imagine there might be a degeneracy with the wind and the fact that faster rotating planets might have other wind patterns. Do you know about that?
So the nice thing is that the winds will probably slow down. Hot Jupiters are likely to have some of the fastest winds just because they are the atmospheres that are being forced the most strongly. And so as we move to cooler planets, I expect wind speeds to be much slower, and so maybe less of a concern.
Yeah, that's right. If you have less of a temperature gradient, I guess you have less winds. Okay, Andrea, you can go on.
Yeah. Hi, Emily. Thank you very much for the nice talk. I have two questions. One is, you know, you said that there is the first eclipse mapping with JWST is coming soon. How many odd Jupiter can be observed in this way? And the other question, which is actually related to Maurice's question, is there any chance we could see this technique applied to close in super Earth or mini Neptune, or they are just way too faint?
Which technique, or both techniques?
Well, both technique, but you know, both the eclipse mapping and the spectroscopic stuff, you know, would be great. Would be great to have a map of a mini Neptune. You know, is that something feasible or is beyond JWST capabilities?
Yeah. So first, your question: how many hot Jupiters? My guess is dozens. I think there are dozens of hot Jupiters that are bright enough, high enough signal to noise that JWST, when making just a secondary eclipse observation, should be able to do some eclipse mapping. If you go back and you get repeated observations of some of these systems, then you could potentially get kind of more detail in those maps. So I think I may be optimistic with dozens, I don't know, but at least a dozen, we'll see. We'll see. I think the answer is that actually we should be getting lots of maps, which is very exciting. In terms of applying either of these techniques to smaller planets, super Earths or mini Neptunes, you know, it's just always harder because with a smaller planet and often a cooler planet, you lose signal to noise in two different ways. But I'm not sure. I'm not sure whether we can eclipse map some of the brighter sub-Neptunes, for example. It might be possible to stack enough eclipses, but I haven't done that calculation. It's a great question. And for high resolution spectroscopy, people are trying to apply it to smaller planets. But again, it's really maybe kind of at the edge of current capabilities. With the ELTs, we should be able to apply it to smaller planets for sure, though.
Thank you.
Right, we have a question in the Q&A by Yasuhiro Azegawa, who says, how does the presence of outflow, mass loss, affect the interpretation of wind properties?
Yeah, this is great. Thank you for asking the question. These are all great questions. So specifically when I've been discussing winds in this talk, I mean winds within the bound atmosphere of the planet. So blowing around at millibar or higher pressure levels. There's also, we expect and observe atmospheric escape from these planets. So in this case, the we call them winds, but they're blowing radially out from the planet. And depending on the wavelengths that we're observing, we are sensitive to different regions of the atmosphere. So near IR measurements are typically more the circulation winds that I've been talking about. But if you go into the optical, some of those opacity sources are so strong that they're more sensitive to these really low pressure regions where the atmosphere may not be hydrostatic. And so then you do get a different sort of velocity component, which is this outflowing wind. And something that I'm pretty confident that the community has not fully figured out yet is what to do when you're measuring some of these lines where you may be in the stronger lines measuring outflowing winds, and in the weaker lines you may still be within the hydrostatic atmosphere. There's been no real thorough analysis of this, although Julia Seidel has been doing some kind of toy models to try to capture kind of whatever velocity components you want in doing fits to things like the sodium and potassium lines, which are quite strong.
Right, that's the last chance now to ask a question to our speaker. And well, I guess if we have no further question, we'll thank Emily again for this great talk.